We did a mixture problem, not this Monday, but the past Monday. And I ended here, and I said, now we know how to solve this using our separable techniques, but I didn't actually do it. I did do it subsequently in my office. I divided to separate, integrated, and came up with our exponential equation, plugging in the proper initial condition. So this was our tank of pure water with salt water going into it, and we were figuring out what happened as time went on. And Monday, I said, when we work with differential equations that are separable, those are directly solvable by integration. But there's an entire separate category called linear differential equations. I'm still just dealing with first order differential equations. If I take my y prime term, and then I have some function of x times y, and then some other function of x, then I have what is called a linear differential equation. And we think of this as linear in the terms y prime and y. The only coefficients of y prime are functions of x. The only coefficients of y are functions of x. Something like the very first differential equation we were working with back in 9.1, where we were just looking at the slope fields. I can rearrange that to look like this. And then I have y prime plus -1 times y equals a function of just x. So here's p of x, and here's q of x. Although it doesn't look like it at first, this particular differential equation is also linear. But in order to make it look right, I want y prime all alone. So I'm going to divide everything by x, and I notice, oh, y prime plus 1 over x times y equals 2 p of x, q of x. That is a linear differential equation. Looking back at that mixture problem from Monday a week ago, sorry, 0.005s. That's also linear if I move this over. Now, I'm pretty sure most of you are saying at this point, big deal. So what? Well, the so what actually comes to me here. Let me go back and look at that side. When I look at that left-hand side, I say to myself, wait a minute. What's the coefficient of y on that left-hand side? Leo? It would be 1. And now I have a great flash of insight because I read the book ahead and cheated. Somebody pointed out to me, hey, look at that left-hand side. You've got an x times the derivative of y. And then you've got y times the derivative of x. That makes this left-hand side the result of doing the product rule. Derivative of the first times the second, first times the derivative of the second, that's the product rule. Wait a minute, that means that the left-hand side is the derivative of what? This is the derivative of a product. The derivative of first, second, that's the derivative of xy. Which means my differential equation looks like this. I have one derivative on one side, and I just have stuff in x on the other side. I know how to solve that. Take the antiderivative. My derivative part goes away. Poof. What happens on the right-hand side?
Become like x squared with constant.
Wait a second. Wait just one more second. I can write an explicit equation. Y equals x squared plus c over x. Oh, it should be x plus c over x. Thank you. Equals x plus c over x. Helps if I write down the right equation. All right, wait a second. I'm going to go back to slopes for a minute. And I'm going to draw the slope field for the differential equation we were just looking at. Y prime equals, clear that. This uses t, not x, so t plus y. Go. So what you're telling me this equation, when x is big, should look like a straight line. Y equals x. Straight, but I should also get that 1 over x thing going on in there somewhere, right? Depending on my value of c, I get things that look like lines, and they look like lines in this direction. Son of a... Ooh. Wait a second. Clear. I wanted to graph this one. 1 over x times y. Wait, so that's y over x y prime equals, oh, there should be a minus sign in front of that. Hang on a second. 2 minus, there we go. Go. Look at that. Look at that. I got a straight line, y equals x, for different values. Now, the reason it doesn't look like slope is 1 is because the scale isn't right. The y-axis is in 2s, the x-axis is in 5s. Let's fix that. settings. We're going to go from minus 10 to 10, minus 10 to 10. Done. Now I see y equals x, don't you? And I see that asymptote 1 over x in the middle, don't you? And the further away I am, the more these look like, oh, there's that 1 over x thing going on. And there's y equals x. This matches exactly what I expected out of this slope field. I have an explicit solution, and I only did one integral. And the integral only showed up because I had a product rule.
So it's the c over x, we should treat it as like 1 over x times c and not like k.
And not like,
Not like it's like a completely different.
right, because the x is not a constant, only the c is. And different initial conditions are going to give me different values for c. I got lucky that I recognized this is a product rule. I don't like luck. I would like to ensure that I always have a product rule. So let me look at our other linear equation. This one. I would like to make this a product rule on the left side. So what I'm going to do is I'm going to multiply by the same thing on everywhere in the equation, on both sides. But I have to pick the something just right. I call this item an integrating factor. I of x. Some books actually call it mu of x. My differential equations book uses mu instead of I. I don't care. I believe this textbook uses I. I'm going to do it first, then we'll figure out where it came from. For this problem, let I of x equal e to the minus x. Then, on the left-hand side, I have e to the minus x times y prime minus e to the minus x times y. And on the right side, I have x e to the negative x. Now, I claim the left-hand side of that is a product rule. Am I talking out my ass? What is the derivative of e to the minus x? Minus e to the minus x. And the derivative of y is y prime. So this is first times the derivative of the second plus, because the minus sign goes with it, derivative of the first times the second. The left-hand side is a product rule. And not just any product. It is the derivative specifically of I of x times y. So this left-hand side is e to the minus x times y's derivative. I now have an equation with one derivative on one side and just stuff on the other side that's all in x. This is the derivative with respect to x. So I'm going to integrate with respect to x to get rid of that derivative. How do I do that integral? Again, unfortunately, u sub does not work here. Why not?
Have to make x to a 1.
If it was a 1, then it would just be a constant, right? But if it was e to the minus x, then the derivative I would need would be a minus 1. Not a minus 1 out front, I have an x out in front. I got to do integration by parts. This is a product, right? Multiplication, x time. All right, wait a minute. That's u and dv, which is, I remember this. This was September. This might even have been August. Oh, shit. All right. Parts. U equals dv equals, all right, wait a minute. LIPET, polynomial comes before exponential. So the u is x, and dv is therefore e to the minus x. And that means that v is minus e to the minus x. Please notice that in figuring out v, Jacob, I did use a u sub there. So I did need a u sub in there floating around anyway. All right, uv minus x e to the minus x minus the integral v du. But the integral of e to the minus x is minus e to the minus x. I took this minus, put it with the minus out front, change my sign again, plus c. And once again, I am in the position to get an explicit solution. Y equals minus x minus 1 plus c e to the x. It would be c over e to the minus, but having a negative in the bottom means it comes up and becomes positive. Okay. Once again, here's my slope field. Y prime equals x plus y. See the line, y equals minus x minus 1? And as x gets bigger and bigger and bigger, this piece gets really big, doesn't it? So we keep getting further away from that line. It's an unstable line, but it's not an equilibrium solution. It's at an angle. Gesundheit. Don't blow your ears out. All right. Talk to me. Questions? Because this process, this always works. Provided I can find that.
Yes, what would you choose?
I was hoping you'd ask that question. Let me go back to the general version, right? Y prime plus P of X, Y equals Q of X. I want to multiply by something over there on the left side. So that whatever I multiplied by here When I multiply by the same thing here, this is the derivative of this. All right, wait a minute. But that means that this derivative on this, in this middle term, has to have the same thing that I multiply by in that circle over there on the left. What's something whose derivative is the same as it with extra stuff? E's, right? E to the stuff, when I take the derivative, I use the chain rule. I get e to the stuff again, and then more stuff. So if I were to let my integrating factor be e to the integral of p of x, then when I take the derivative of I, the integral of e to the stuff is e to the stuff plus the derivative of the stuff. And since I used an integral up there, when I take the derivative integral, I get the stuff back, don't I? Holy crap. So in my equation, p of x is minus 1. So the integrating factor is e to the integral of minus 1 dx, which is e to the minus x. Holy crap. Wait a second. Remember, this is the one where I said I recognized the left-hand side like it was a product rule. I'm going to be blind to that. I want to redo this problem without knowing that that left-hand side is a product rule. And so I say to myself, to make this linear, I have to divide by x. Right? Okay, boss. P of x, q of x. If this is p of x, what is my integrating factor? It's e raised to the integral of 1 over x dx. Integral of 1 over x. ln of x. So I get e to the ln of x. What happens when you have e's and ln's together? They cancel right out. My integrating factor is just x. So I multiply by x, and where does that put me? Right back where I started. And that means that this left-hand side is the derivative of this times y. It's the derivative of a product. Even if I hadn't recognized it, that's what it has to be. The derivative of the integrating factor times y. I love integrating factors. As long as I can actually do the integral of p of x. My goal is to never have that F me over. Now this one's already started in linear form. y prime plus p of xy equals q of x. It's exactly the right format. Let's go to town. Leo.
I was thinking p of x would be 3x squared and q of x would be 6x squared.
Exactly. So I don't have to do any division. All I have to do is write my integrating factor. My integrating factor is e to the integral of 3x squared dx d to the x cubed. E to the x cubed times y prime plus 3x squared e to the x cubed y equals 6x squared e to the x cubed. Now, a lot of people are bothered, and I usually get questions, why did you put the e to the x cubed in the middle there? I always put the derivative of the inside out front when I'm doing e's. It's just force of habit. It's not required. But e to the x cubed, the derivative of the stuff is 3x squared. That makes this the derivative of this, and that means that this left-hand side is the derivative of e to the x cubed y. But also note, the derivative of the x cubed is 3x squared. Over here I have a 6x squared. And in order to get rid of this prime, I need to do the integral of 6x squared e to the x cubed dx. Jacob, now, what do I do? Exactly. U equals x cubed, du equals 3x squared, so I'll get 2 du. But notice that over on the left, it is still e to the x cubed y. So I have to divide that integrating factor to get y all alone, and I get 2 plus c e to the minus x cubed. Talk to me, Manny.
What happened to the 3x? I know that is that product, but like what happened?
Derivative of the first times the second, derivative of the second times the first.
Oh, so you're saying that whole thing is the derivative? Okay.
That whole 4-bit is the derivative of this 2-bit. Hey, wait a second. What happens as x goes off to infinity? Yeah.
When you approach zero, it's a negative infinity.
But that just means this term is approaching 0. And that means overall, my solution is approaching 2, which means I have an equilibrium solution. Things get closer to it.
So we get this y as 2.
Right. But that means if I looked at the equation and its corresponding slope field back here, three t squared times y plus 6t squared. What the hell? Oh, wait. I thought I was multiplying in the power. Here's my equilibrium solution. As I go off to this side, things converge to 2. What happens over here when x goes to minus infinity? All hell breaks loose. Because when we go to the left, this becomes e to a very large number, and e to the big number is very big. So we are converging to a stable equilibrium as t goes off to infinity. Questions? Remember the electric circuit example? This is the one we did last Monday before break. And we did it by integrating, by separating, right? We separated, divided by this, did a u substitution, and I said that works. And that's very similar to the mixture example. We divide out, we integrate, and all of that, right? But because I now have this other idea, I can use linear techniques instead. If I move this 3i over, what's my integrating factor?
E of x 3 and my q of x 15.
So my integrating factor is e to the,
E to the inverse 3, e to the 3x.
I want to use t instead of x here because I'm dealing with time and it shows t is my independent variable there. So I'll do e to the 3t. But that makes this e to the 3t I prime plus 3 e to the 3t I equals 15 e to the 3t. Maddie, the left-hand side, derivative of the second times the first, derivative of the first times the second, is the derivative of e to the 3t times I. So to get rid of that, I take the integral of 15 e to the 3t dt. Wait a minute. This is another u substitution. U equals 3t, du equals 3 dt. I have a 15. When I divide by the 3, I'll get a 5. E to the 3t I equals 5, e to the 3t plus c. I now divide to get I all alone. I equals 5 plus c e to the minus 3t. Because I divided by e to the 3t. Wait a minute. There's an initial condition up there at the top of the screen. I of 0 equals 0. So when I put in t equals 0, what's e to the 0? That's not supposed to stump the room. Ta-da! My current equation is 5 minus 5 e to the minus 3t. And if you go back to last Monday, that's the exact same equation we got then. Only I didn't need to do a bunch of redividing. Now, if you remember this setup, this particular problem, there was a lamp and a resistor and a switch and a battery. How many of you have battery operated lamps in your room? My lamp plugs into the wall, right? If my lamp plugs into the wall, then it's not using direct current, it's using alternating current. Alternating current works like a trig function. Instead of pushing the electrons through the lamp, it causes the electrons to shake back and forth through the lamp, lighting up the filament. But that means over here on the right, I wouldn't just get 15, I'd get the trig function for the wall current. And I happen to know wall current at whatever voltage operates at 60 hertz. So I should get why 30? Well, technically it should be 30 over pi because it should be a period of 60 cycles per second. 2 pi divided by 6. Yeah, I'm going to get a factor of 30 floating around in there. But if I go through the same process, my integrating factor is e to the 3t. Which means over here on the left, I end up with a derivative. In order to get rid of that derivative, I have to integrate. I have to integrate e to the 3t times sine of 30t. The appropriate answer to that is not just no, but no. I'm not doing that. So I go back to the table of integrals in the back of the book, and lo and behold, table formula number 98 is exactly what I want. It's e to the at sine bt. I go to Wolfram Alpha, I plug that left-hand side in. I don't have to do this by hand. Isn't that just disgusting? I didn't make it up, though. That's the formula out of the back of the book, people. I promise I did not come up with that on my own. There's no way I could have come up with it on my own. By the way, to do this problem by hand requires you to do double integration by parts. And then you end up back where you started, so you have to move it to the other side. No, just no, it ain't worth it. But now I have an equation. By the way, I divide out that e to the 3t. I equals 15. The e to the 3t here cancels that one. So I get over 909 times 3 sine 30t minus 30 cosine 30t plus c e to the minus 3t. Isn't that just disgusting? But alternating current should look like a trig function, shouldn't it? That's the definition of what alternating does. It moves back and forth in the electric circuit coming out the wall. That's why you have those power blocks for your phone and your MacBook and your iPads. Those charger blocks turn alternating current into direct current, so it can get pushed into your battery. A one-directional current flow. But now I can say, oh, if I do more complicated mixing problems, or problems that I could not do just by integrating, this becomes much simpler. And the use of integrating factors now allows me to solve much more general types of equations far easier. I would point out to you two things. Because you are always going to do e to the integral of something, you will often need to use tricks for the integrals, and you'll need to remember about properties of logarithms. Back in this problem, I canceled out the e and the ln, yes? Let me change the problem ever so slightly. Instead of doing xy prime plus y equals 2x, I'm going to do xy prime plus 2y. Huge change. Huge. What happens? Walk me through the integrating factor setup.
Divide everything by x.
I must first divide everything by x to make it look like a linear equation.
I make p of x 2 divided by x, and q of x equals 2.
So my integrating factor is e to the integral 2 over x dx. The integral of 2 over x
2 times and that's y and that's divided by x.
because I am considering what happens with the absolute value in terms of the constant I end up with at the end. I don't need it here. I can't cancel the e and the ln. They're not next to each other. Leo, what property of logarithms do I need to use?
Should be an e to the x squared.
Careful. It's e to the ln of x squared because numbers become powers with logarithms. Now the e and the ln are next to each other, so my integrating factor is x squared, not x. Okay, go back up here, multiply through by x squared y prime plus 2xy equals 2x squared. Now this is the derivative here, and this is the derivative here. I have a product rule. Ta-da! In my previous problems, I didn't give you an initial condition. I'm going to give you an initial condition after we solve this. X squared y equals the antiderivative of 2x squared is 2/3 x cubed plus a c. I divide out the x squared, y equals 2/3 x plus c over x squared. And now if I were to say that y of 1 equals 1, you could solve for the proper value of c. And I get c equals 1/3. Questions?
So is there a reason it's like y0, 0, y1 equals 1, or is it just?
I just pulled it out of thin air.
Okay.
You want to do a different one? Y of 1 equals 7? Do whatever number you want. I literally just, I knew I couldn't use 0 for x. Why couldn't I use 0 for x? And notice that when I set up the problem to be linear, I divided by x. So I knew right here that there was going to be an asymptote at 0 in all of my solutions because I set it up that way. Those are called singular points for my differential equation. And there's a whole treatment of how to deal with singular points in the differential equations class and in more general treatments of differential equations. That's why I picked y of 1. And then after that, I'm like, well, what's easy? 1 is easy. Most of the time, they're not the same. I just felt like it. Other questions? Okay. Again, there's a whole course of differential equations. More often, we use higher order differential equations. First order differential equations are very well treated this way. But second order differential equations are far more common in physics, engineering, biology, chemistry, medicine, and all of the places where we actually use differential equations. Second order comes up much more often. That's what I'm going to talk about on Friday, because tomorrow is question and answer day for 9-3, 9-4, and 9-5. I will see you all then. Have a wonderful rest of your day, people.